you very much. And some of you are still ready to hear about experimental systems and nanomagnetism. Good. So I'm going to tell you about ways of driving magnets out of equilibrium. Oh, my phone. Yes. So you really want to hear about
The webcast
Please do the ring.
Is that on?
There are two switches. Yeah.
Yeah, should be on now.
Oh, now is it on?
Yes.
Yes. Okay, good. Okay, so I'm going to tell you about a way of driving magnets out of equilibrium using currents, spin currents, instead of magnetic fields. This is a really growing area in the investigation of magnetism in small magnets. It's associated with the fact that magnets that are these magnets like nickel, iron, cobalt, these transition metal materials are conductors. So if you flow a current, you have actually a flow, not only if you apply a voltage to a ferromagnet, not only do you have a flow of charge, like you have in any conductor, but you also have a flow of spin. You have a flow of spin angular momentum, and so you have a way of influencing the spin through the flow by applying electric fields. That's fundamentally what's going on. And the field started basically with the discovery of giant magnetoresistance. So I'll give you a very basic introduction to giant magnetoresistance. I'll motivate why there should be an interaction between the current and the magnetization, basic conservation of angular momentum. And I'll tell you about a spin momentum transfer. And then we'll see a simple way to consider this, is to add a term to the Landau-Lifshitz-Gilbert equation, which you saw this morning, which describes this new interaction. And that's, we'll call it the LLG plus S. S for spin torque, or S for Slonczewski, who first proposed this form of interaction. And you'll see that there's a threshold current for exciting the magnet, and you can get hysteresis, current-induced hysteresis. So the same things that happen in magnetic field now happen with currents. And I'll show you experiments that are the first evidence for this effect, which were in point contacts and very small magnets, nanopillars, a little bit like the nanopillars you heard about this morning. But these are, and then I'll show you the transport results, noise, and high frequency characteristics, which show some of the real essential physics, I think, of what's going on. And I'll mention one word about why there's so much excitement in this, in terms of making new types of magnetic memory, magnetic random access memory, where you would use spin currents instead of magnetic fields to change the state of the memory. And I'll summarize and then I'll give you references to this area. So the story begins with the discovery of giant magnetoresistance. Giant magnetoresistance was discovered in metallic multilayers, ferromagnetic non-magnetic multilayers. And what was discovered is that when you apply a magnetic field to a layer that initially is where the layers are oriented anti-parallel in an anti-ferromagnetic configuration, the resistance drops significantly when you reorient the layers into a parallel configuration. So this was the experiment done in France in the group of Albert Ferd, and they saw a 50% change in resistance at relatively high fields in an iron-chromium multilayer with 60 repeats of the layer. And at the same time, the group of Peter Grunberg in Jülich saw in a tri-layer structure, in an iron-chromium-iron tri-layer, saw a modest change of resistance, 1.5%, in a much smaller magnetic field. And this was the birth, I guess, of the field which is called spintronics, spin transport electronics, in which you can control the current using the spin of the electrons. So the magnetic configurations of the layers determine how much current can flow through such a structure. And we'll just look very briefly at GMR. This is a GMR stack consist of metallic layers separated by magnetic layers separated by non-magnetic layers. So cobalt, copper, cobalt is a typical structure. And if you apply a magnetic field and you start, say, with the layers both magnetized to the left, in some range of field, you'll reach the coercivity of one layer, and the layers will be aligned anti-parallel, and then you go a little bit higher and you'll reach the coercivity of the second layer, and the layers will again be aligned parallel. In that region where the layers are anti-parallel, there's a higher resistance. And you can repeat that, go back, start from both layers magnetized to the right, and you see the mirror image of the resistance curve. So what's the basic explanation? The basic explanation is associated with electron scattering in ferromagnetic materials. So in a non-magnet like copper, you have an equal density of up and down spins. There's no net magnetization. But in a material like cobalt, there's an imbalance between spin up and spin down. There's a different number of up and down spins. That's basically the origin of magnetism. It's the spin magnetic moment, the difference in the total number of up and down electrons. And at the Fermi energy, there's different density of states. Different density of states, also there's different scattering rates for electrons that are aligned with the magnetization and those which are anti-aligned, for what are called majority and minority electrons. And so if you, as I mentioned earlier, if you apply an electric field, you'll get a flow of current, but there will be a difference in the current between electrons aligned with the magnetization and electrons anti-aligned. In general, the electrons which are, say, like in this case, it's really the electrons which are minority electrons would have a larger resistance than majority electrons. And the picture then is you have two electron channels. If you have these two magnetic layers now separated by a non-magnetic layer, one channel will have a different scattering rate than the other, and if the layers are aligned parallel, that channel can provide a short circuit. These electrons that are majority electrons can travel with longer mean free paths, longer scattering rates through the layers, whereas the minority electrons will be scattered in the layers. So you might have a resistor model like this, where the majority electrons have a low resistance and the minority electrons have a high resistance. And then when you reorient the magnetic layers, you've blocked, you have scattering of one channel in one of the layers and the other channel in the other layer, and you have a picture like this. So you have the giant magnetoresistance resistance effect can be thought of as a short circuit, whereby a low resistance channel provides a path for conduction, and this gives you the resistance changes you typically observe at room temperature, which are 1 to 10% for bilayer structure. So this is the basic picture, is scattering of the electrons, and this is the two-channel model. Actually, this model originates with Mott, with Mott's trying to understand the properties of the conduction and transition metal materials. And he came up with this idea that you have two channels. What GMR gives you is a means to control the conductances by basically reorienting these layers from parallel to anti-parallel. So the non-magnetic layer here plays a kind of passive role, just allowing you to decouple the layers, to reduce the magnetic interaction so you can reorient them with respect to one another. Okay, so a simple picture is you can also think about this as spin filtering. You can think about you have an unpolarized set of electrons coming incident on a ferromagnetic layer. Because of the scattering in the layer, some of those electrons, or more electrons of one type, are reflected, and more of one type are transmitted. So you end up with a spin current. And then the second layer also acts as a polarizer. So if the polarizers are aligned, you get a greater number of electrons per unit time flowing through the layers. Yes?
So can you tune the layers in such a way by, for example, adjusting their thickness so that you basically block all the spins of one polarization?
If you had a material that was completely polarizing, So 100% effective, you could do exactly what you're
So the
saying.
polarization is not. So the polarization ability of the layer is not related to the thickness of the layer in any way.
It's related. At some, well, there are two. I guess it's not related to the thickness of the layers, because you have both. I mean, in these ferromagnets, you have channels at the Fermi level for both spin up and spin down. And there's the other thing that's missing from this picture is you have spin relaxation. So at long length scales, there's spin flip scattering. So at some length scale, you lose. And as you equilibrate, at longer enough length scales, the spin currents become equilibrated when you get up to what's called the spin diffusion length. So that length for these ferromagnetic materials is on the order of 20 to 40 nanometers. So thin layers are essentially effective, but at some long length scale, you have spin flip scattering, which reduces the spin currents in the layers. That's a very good question. In fact, much of the scattering is actually even occurring at interfaces of these layers, not even in the bulk. At the interfaces between the magnetic and the non-magnetic materials, you have spin-dependent scattering. So this is a very simple picture of what's going on, but I think it captures some of the physics. If you have the layers anti-aligned, you see that one channel can propagate, but is blocked at by the second layer. So overall, you get a smaller number of electrons passing through these layers, and so less of a smaller current, and also you have no spin current at the end of the day. Here you have. At the end of the day, you have a spin current. You have an imbalance between the electric current of spin up and spin down. So this is the very basic understanding, and you can understand giant magnetoresistance through what this was called so-called two-channel model, and that was the state of the field until 1996. And in 1996, there was the idea that if these layers act as polarizers, there also must be a back reaction on these layers due to the flow of spin angular momentum. So the idea is that if you put an electron, say, spin up through the layer, and it's filtered so that it comes out predominantly in the direction of the magnetization of the layer, then there's a change in the angular momentum of the current, and by consequence, there has to be a corresponding change in the angular momentum of the background magnetization to conserve angular momentum. Kind of a very simple idea, and yet it was only recognized well after giant magnetoresistance. There are actually seeds of this idea in a paper that John Slanzewski wrote in 1989. John Slanzewski is a scientist at IBM Research who's worked many years on magnetic materials. He considered a magnetic tunnel junction, two magnetic layers separated by an insulating layer, and he did basically the rectangular barrier calculation for a tunnel junction, and he showed that when you bias the tunnel junction, you change the magnetic coupling between the layers. That's a kind of, so there's coupling between two magnetic layers through a tunnel barrier, just like there can be transfers of charge. And he also saw there was a non-conservative part to that coupling. That non-conservative part is the spin transfer interaction. So that's a very nice paper to read to get an idea of where this comes from microscopically in a simple situation. So the idea is that if you have this filter and you have that something, there should be a torque. And so if you were to reverse the sign of the current, you would reverse the sign of the torque. Conservation of angular momentum. So the thinking is, what happens if now you have a situation like you do in a multi-layer, where you have two magnetic layers separated by a non-magnetic layer? Imagine this is a very big layer that sets the polarization of the electrons in this intervening non-metallic, in its non-magnetic layer. So electrons come in, they become polarized, and they interact with the second layer, and they come out with with their polarization in the direction of the second layer. Then, by conservation of angular momentum, this magnetization experiences a torque which tends to rotate it counterclockwise toward the direction of the fixed layer. So if you have spin currents moving to the right, you'll favor a parallel alignment of the layers. And in the opposite case, when you spin currents moving to the left, the torques are in the opposite direction, you'll favor an anti-parallel alignment and a high resistance state. So the first thinking is that if you have this multi-layer, by changing the direction of the current, you should be able to favor one or the other of the states, parallel or anti-parallel.
What's the difference between the layers with thermistics and 3 here?
So one is just bigger, thicker, has a larger moment, a larger angular momentum. So there are torques on both layers, but if one layer has a much bigger angular momentum, it will take a lot more torque to move. It's like a massive object and an object with a smaller mass. But in practice, what you can do is you can choose a material with higher coercivity. You can choose a material which is coupled to an antiferromagnet to raise it, to harden it. There are many ways you could realize this situation. In fact, if the two layers are identical, these torques still exist. And there's a very interesting, in fact, in the 1996 paper, Slanczewski showed when the two layers exist, and both have the same characteristics, they will both tend to rotate in the same direction. So if you're thinking, well, that one layer is transferring angular momentum to the other, you might imagine that they counter-rotate. That's not really what's going on. They would actually their motion would be like a windmill. Both would be processing. It would both be processing in the same direction. So that you have to look carefully at Slanczewski's paper to figure out where that comes from. Where does the angular momentum come from? And it's an interesting exercise, actually, to try to understand where the angular momentum is coming from. We're saying angular momentum is conserved, but where is it coming from if both layers are rotating around in the same way? Someone can tell me at the end of the lecture. I'll be extremely impressed. It'll just be a week to figure that out. So anyway, and the other thing to note is that this is predominantly, at least the majority view, I would say, if we went on almost consensus, is that most of the transfer of angular momentum is occurring at the interfaces to the ferromagnetic materials. Why? Because the electrons of these two types of electrons spin up and spin down on very different Fermi momentum. Okay, so that basically you can't maintain coherence of an electron that has some arbitrary superposition of the magnet. The other thing is you're averaging over all the electrons on the Fermi surface, and that also reduces the coherence through dephasing of the. So it's if you write down the wave functions as terms of a spinner times EPIK X, you'll see that the phases oscillate, the two components oscillate, and that decays on this kind of length scale.
What is the mechanism for this spin relaxation?
So the spin relaxation, the mechanism is an exchange interaction. So as the electrons go into the ferromagnet, they feel the exchange field. So that's a very large field. That's the scale of that's the delta is the scale, you'd say, of the ordering temperature. That's about 100 Tesla. So they process very rapidly a new phase on this scale. I guess one model would be a Stoner model of the ferromagnet, which would give you that length scale. So this paper is called The Anatomy of a Spin Transfer Torque, and describes a lot of that, what's happening and where the angular momentum is lost. There's a minority view, which I have to mention because one of my colleagues has it, Peter Levy, that this actually occurs over a much longer length scale in the ferromagnet, but we don't know that yet, really.
Can you control the coherence length by doping your layers?
You could potentially make it much larger by using what's called a weak ferromagnet, which has a much lower ordering temperature. So if this is set by the difference in Fermi momentum, if you have something where the exchange splitting is much smaller, you could have a much longer coherence length for the transverse component. In a metal, that would mean actually looking at a metal which has a lower ordering temperature, or you could go to a material like a magnetic semiconductor, where the length scales are much longer. So there would be different ways to control this, material ways to look at this.
Also, there will be some relaxation within the non-magnetic layer of something that produce that.
That's right. There's also spin relaxation in the non-magnetic layer. Spin flip scattering also reduces this effect in the non-magnetic layer. So this layer usually should be smaller than the spin diffusion length in the layer to maintain the spin polarization in that layer.
So in this case, the interaction is mainly the exchange interaction.
It's the exchange interaction. It's the exchange interaction between itinerant electrons and background magnetization. So it's unusual in that you usually think about exchanges between sites I and J. Here, the same electrons that are responsible for the magnetism are also conduction electrons. So you don't have this neat separation into localized and extended states.
So then in the second picture, when the neutron space like the free magnetization will to infrared direction. This means this is the magnetization will can also couple to the orbit of the electrons.
The orbit of the electrons.
The orbit of the electrons. It looks like.
Looks like it coupled to the orbit of the electron.
Because this means the free magnetization can distinguish the forward movement and backward movement of the motion of the electrons. Of course, although this picture can be understood as a time reversal process of the first picture, but
yes.
There's this strange because it seems the magnetization can couple to the orbit of the electron.
It couples. Yes, it seems that right now in terms of that's right. There's a difference between states propagating to the left and propagating to the right in terms of this coupling. Now in equilibrium, there's also coupling. There's an equilibrium exchange interaction through the non-magnetic metal, the RKK-Y interaction that goes through. So here by applying the bias, you're breaking that symmetry between up and down. You don't have equal numbers of up and down, left and right electrons. But as soon as you apply a bias, you have a net flow. That breaks the balance between these pictures, I believe. So there's a battery here that's pushing electrons one way. You have a net flow one way or the other. Okay, so I think this is going to be in textbooks. It's not. We don't teach this at all. But it should be in textbooks. I mean, because before Sadzinski proposed this, the only way we could change the direction of the magnet was to apply a magnetic field. And that requires that you flow a charge current somewhere. So if you have a flow of charge current, you can reorient the magnet. And now, what Sadzinski showed along with Berger is that you can flow a current directly through a ferromagnet and exert forces on the magnet. And those forces are associated with the flow of spin angular momentum. Of course, if you flow currents directly through the layers, you also have flows, charge currents. So you have both magnetic field and spin current flows. There have been some nice experiments there which have shown that you can separate the spin and the charge and show that it's really the spin current interaction that's setting the scale of what's happening in these layers. So this is actually giving us new insight into the transport of spin, and I think key for this audience is there are really new types of magnetic excitations. And so to give you an example, if you flow a charge current, a steady state charge current will generate a steady state field, constant fields. It can vary spatially, but it's constant in time. If you have a magnet that's experiencing that field, there might be some temporal response, but if you wait long enough, it will eventually readjust itself to the new field and come to a new minimum in the energy. and in some stable configuration, some static configuration. Now, in a steady state spin current, what can happen is the magnetization can end up in a precessional state, where there's a time dependence to the magnetization. So that's one of the fundamental differences. Steady state charge current can only lead to kind of a new static state eventually, whereas a steady state spin current can lead to dynamical excitations of the magnetization, which have been seen, and which I'll show you have been seen in experiments. And this is the teaser. Most of the theories are really untested in the sense that we have a phenomenological theory. What's missing is sort of a microscopic understanding. And the other aspect that's missing is, I think, your community understanding the non-equilibrium dynamics of these systems, because it's not clear. Now you have a system that's open, it's connected to reservoirs, and the fluctuations, we don't understand the fluctuations in these systems and reversal in these systems very well. So that's I think, an interesting aspect to this.
So you mentioned this precession,
Yes.
right? And my question was, I thought you had said earlier that precession gets damped out, or am I to understand?
No, you're absolutely right. I said that actually. Yes, I said that when I was speaking about the Landau-Lifshitz-Gilbert equation. I said we have this alpha, and Pierre also said this morning. And eventually, these precessions are damped out.
Okay, so
what I'm saying now is there's something else we have to add because these precessions aren't damped out.
So we could think of them in the classic case of a non-equilibrium steady state.
Yes, we reach a non-equilibrium steady state.
All
Exactly.
of the work theorems that are associated with that.
I'm not sure. But we do reach a new type steady state, which is a dynamical state of the system.
Yeah, but it's not a non-equilibrium steady state because actually the magnetization is changing with time. So it's approaching like a precession cycle. So
Yes.
the distribution of magnetization processes all the time. It's not steady in that sense.
It's not a problem, it's all more complicated steady state.
Yeah.
Yeah, but the distribution of probability doesn't depend on time, right? In a steady state.
No.
The currents depend are non-zero, but you have a distribution dependent on time. In this case, you have a distribution that is time independent but it changes periodically.
Yeah, and you see this sort of thing in biological systems. And you can hear the non-equilibrium steady state. So the same math should work.
The thing. I agree.
Okay, so this is the new ingredient we have to add to our dynamical equation to capture some of the phenomenology. So this you saw yesterday, and I was up to here, and everything was damped out by this term, the alpha m plus the dt. And this is the new ingredient that was proposed. Basically, it's a term that depends on the polarization direction of the current, MP, and on the current. Aj is a factor that's proportional to the polarization of the current and the current density that's flowing through your magnet. So let's see. The first thing to say is this is indeed what this expression says is that the transverse component, the component of polarization transverse to the magnetization, is absorbed by the ferromagnet. And that means that so if you have the magnetization at some angle, if the polarization were along the direction of the effective field, then the torque will be collinear with the damping. It will be in the plane containing M and the polarization, and in such a way as either in the case where these two vectors are aligned, either to enhance the damping, or to lead to a faster return to equilibrium, or to lead to a greater degree of excitation with the magnetization. So here you can see how you can achieve a steady state if you balance the dissipation with this interaction. And this is a non-conservative interaction. It can't be written as an effective field. It's changing the energy of the system. It's changing the projection of the magnetization on the field, so it's changing the energy of the system. The natural units of this are h bar over 2e. So each electron can at most deposit h bar over 2 of angular momentum into the magnetic layer. And that would be a perfect efficiency for this transfer of angular momentum. So you can also, there's also possibilities to have a term that goes as a Bj times m cross md. This is called an out-of-plane torque. This would be a torque perpendicular to the plane containing the polarization and mp, and proportional to the current. This is sometimes called the current-induced effective field. This could be lumped in with the which H effective, and would change the precession frequency. This term turns out to be not as interesting as this one because it can't lead to anything you don't have with magnetic fields. It can change, but so most, in fact, it's been shown that this term is fairly small in metal systems, and it, at least in all metallic systems, it can be important in certain situations in magnetic tunnel junctions. But we can focus for the most part on this interaction. So this interaction competes with the damping. When the current achieves a critical value, you can have dynamics. So basically, the current has to be large enough to compensate for the damping. So there'll be dynamics at a critical current set by the geometry.
Can you think of that as a proper phase transition?
Can you think of it as a phase transition? Okay, so far I'm thinking about this as, I don't think so, because I'm thinking about this now as a system with just a few degrees of freedom, and I'm asking when is that system going to execute some different motion, essentially. So I don't think you can think about it as a phase transition.
So here the threshold of the current should be proportional to the damping coefficient.
That's right. It's proportional to the damping coefficient and also the frequency of precession. So it's proportional. I'll write down the expression on the next slide. It depends actually on the forces in the ferromagnet, the energy of the ferromagnet, the micromagnetic energy. And most of the time we're working with very thin elements. So we work with very small sections of thin films. We call them nanopillars, but we should really, to distinguish from the talk this morning, we should call them nanopancakes, because they're only a few nanometers thick and 100 nanometers or so wide. And so the magnetization is confined to the plane usually confined to the plane of the element. And there can be also anisotropies that lead to a preferred direction. In this case, I picked the x direction to be preferred. So this is the largest anisotropy. Usually, if you don't do anything special, the magnetization is in the plane and then has some preferred direction. So just to show you, this is the picture then from my collaborator Jonathan Sun of what the dynamics will look like. You have a nanopillar. You have something that's, I'll say in a moment why you pick a nanopillar. It's about 100 nanometers wide. Electrons traverse this layer, and if the current is below the threshold, the magnetization simply decays to equilibrium and spirals in like it would if there were no current applied. If the current exceeds the threshold just barely, the magnetization will spiral outward and eventually will reverse. So you'll go from the North Pole to the South Pole. And if the current is significantly greater than the critical value, this will happen much faster. So it will happen in a few precessional cycles rather than in hundreds. So there's a critical value of the current, which depends on alpha, depends on the polarization. So this has some of the characteristics you might expect. If the damping is very large, the critical current is very large. If there's no polarization, the critical current is infinite. So it depends on having a spin current. And then this you can think of as the frequency of precession. This is essentially the frequency of precession of the magnetization. This times gamma would be the frequency of precession. And yes. Okay. Please feel free to ask questions. I realize this is probably, this is maybe completely new to you.
So your excitation, if it's large enough to flip the spin, it still damps the precession back to the spin flip state.
Oh yes, you mean if it does it end up here, does it end up going around and around?
Yeah.
For one direction of the current, you end up in a new state. So there are 3 possibilities. You stay in at least for one of these, for a macro spin, a single domain. You can either stay in the initial state, you can go into a precessional cycle, or you can go into the reverse state. Okay.
Can I see the current in connection with figure B there?
No, you can see that the black curve is for a curve that's subcritical. The green curve is just above the critical curve. I believe. Let's see. We should follow this. It looks like it. And the red is far above the critical curve.
Which direction does the current go?
The current, let's see. The electrons are moving. I believe. Let's see. To get an instability, the conventional current must be to the right. So positive current would be considered flowing to the right. Electrons are flowing to the left. Actually, no. This is not the way. This is wrong. With the polarizer fixed. No, this is right. Right. To get a instability. This is drawn correctly. So electrons moving from left to right will produce this instability. You would go from, assuming that you're starting here in an anti-parallel configuration, you end up in a parallel configuration of the layers.
So can you measure the heat dissipated in the magnet as you process these spins?
As the heat dissipated, it's difficult to measure the heat dissipated in the magnet just because they're such tiny objects. And a lot of the heat is dissipated, and they're connected also to some pretty massive leads in the experiment. So there's heat dissipated not only in the magnets but in all the adjacent layers. It's hard to measure the amount of heat in the nanomagnet itself. You want to know how much energy is being
right now how much energy is being fled out of the system.
Yes. Let me show you some of the experiments, and if we can come back to other things.
Is that related to like T1, like decay of magnetization?
So T1 would be related to the spin diffusion length. So that would be the longitudinal component. This is the transverse component. T2, the T2 process would be more in line with this, but it's not usually spoken in terms of those languages. T1 there's a close analogy between T1 and the concept of spin relaxation, longitudinal spin relaxation, and usually people don't speak about T2 in terms in this process. Because this is, at least this is viewed as a dephasing process.
I'm just thinking like you have a vector and it's decreasing in magnitude and then increasing in other direction.
Oh, so the oval vector is on a sphere. So again, we're taking the Landau-Lifshitz-Gilbert approach that the size of the moment doesn't change, only its orientation. So it's relaxing from up to down, but its magnitude is constant. Okay, so these are the kinds of stability diagrams you can find. They depend very much on the details of the magnetic structure. You have 2 magnetic layers that are aligned in the plane with the anisotropy I showed you earlier. You would get a diagram like this. So this is a field current, and these are the possible configurations: parallel or anti-parallel, and PS means precessional, some kind of precessional state of the layers. So you're familiar with this cut, saw that this morning, where you measure magnetic hysteresis. So you go from, if you assume that one layer just has a fixed direction, and as you sweep the magnetic field, you would go from anti-parallel to parallel. And what state you are in between would depend on the previous history of the magnet. Now, you can do the same with current. You can start in a parallel current configuration as you sweep the current. At some critical value, you would switch to an anti-parallel configuration. When you come back, you would switch back to the parallel configuration at at the opposite, a current of opposite sign, or on the negative side. So you have a region here of bistability where you can switch the magnet with a current. I won't talk about, these kind of stability diagrams I mentioned depend very much on the form of the anisotropy. It's enough to know that, you have these kind of stability diagrams. And there are regions also in this space where there's precession of the magnetization. Okay, so why do you have to do this? Why are these experiments done on very small structures? It's supposedly a general phenomenon. You apply a current to a magnet and there should be torques now on the magnet. The reason is that practical and also physics. Practical is that you can't apply big enough currents to these elements without causing them to melt. They're fairly large currents. We're talking about 10 to the 6th to the 10 to the 8 amps per square centimeter. That's a pretty big current. So if you had millimeter scale structures, you'd be talking about applying huge currents and the samples would just melt. And the other reason is that magnets respond to magnetic field. So when you pass a current, you have both charge and spin, and so you have a magnetic field, an Oersted field. And we know the magnets respond to some critical field. So that in terms of current, that means there's a critical current that depends on the radius of the area through which the current flows. Now the spin-torque interaction depends on is an interaction where there's some dynamics at a critical current. And so that current, the threshold current where that happens goes as the radius squared. So if you plot these then, you'll see that if you're at small enough radius, you would first have the dominant threshold would be determined by the spin transfer interaction, whereas if you make these structures much, much larger, you would be dominated by the magnetic fields. So where that crossover occurs depends on the materials. And for example, if you take cobalt, you'd find that you really have to work with something with a diameter less than a half a micron in order to have these spin currents dominate over the effects of charge currents. So you need to have small structures, nanostructures, in fact something less than 250 nanometers to explore this interaction. I just want to mention that this is a field that's taken off in the sense that this is a very general phenomena that occurs in many different types of magnets. It's not limited to transition metals. It doesn't just depend on switching magnetic domains. You can also move domain walls with the spin current interaction. So this was the first theoretical work in 1996, and the first experimental work the first demonstration, I guess, was right in here, where the difficulty was essentially fabricating the samples. The first point contact experiment was here. We can see this is taken off because there are many kinds of materials that you can use in structures. It works on point contacts, nanopillars, nanowires, nanorings. You can use spin valves. These spin valves are all metallic samples, multi-layers. You can have a magnetic tunnel junction. You don't even need two magnetic layers. The effect works even when you have one magnetic layer. You could work on metallic it's important in metallic ferromagnetic magnets, magnetic semiconductors, even anti-ferromagnets, oxide ferromagnets, and the phenomena are current-induced switching and precession and current-induced domain wall motion. I don't know if any of you have heard about this idea that IBM has to make racetrack memories. Have you heard about this?
Yeah, I read about it at about 40 times.
I mean, I've already heard the talk about 100 times. It shows that. So it's okay. So Stuart Parkin has a patent with the idea of basically replacing. I don't know. The students are probably too young to remember magnetic tapes, cassette tapes, where you move the magnetic material past the head and read it. You have it in that camera?
Yeah.
Okay, good. It's not just. Are you sure it's not a card, memory card?
It's memory. It's a magnetic tape.
It's a magnetic tape. Okay, good. So the idea of the racetrack is instead of moving the magnetic material, just move the magnetic domain walls. Keep the magnetic material in the same position and use a current to push the wall, so you have no moving parts. Current is going to do just move the magnetic information. It's kind of cool. It's a great idea if it would be a way of really storing a lot of information on the scale of a magnetic hard drive with no moving parts. So that lots of people are working on that. The physics is current-induced domain wall motion, and all of the issues associated with stability of domain walls, thresholds are important in this area. If you haven't heard the racetrack talk, I highly recommend it. There's a YouTube on it. You can look at racetrack on YouTube, and here's Stuart Park and talk about a racetrack. Okay, so that's enough advertising. These are the first experiments on spin transfer were simple experiments. People took a multilayer and they put a tip into the multilayer. So to have a high current density, this is a well-known way of doing spectroscopy. And this was done in Grenoble first by Maxime Soy. And what he saw is that for one direction of the voltage current, you saw there was nothing happened in the differential resistance. Whereas in the other direction, you saw blips in the differential resistance, which move to higher field as you move to higher voltage as you increase the magnetic field. That was taken for some evidence for some kind of dynamics, not clear exactly what. The other experiment that was done was to take a nanopillar, a nanopancake, thin layers that were a few nanometers thick, 3 nanometers and 12 nanometers, and to ramp a current. And you could see a curve that very much looks like the magnetic hysteresis you'd see on a magnet. When the current reaches about 2 milliamps, the resistance jumps, and when you come back, it jumps down to the lower values. And then they could show in this experiment, which was done first by the Cornell group, that the resistance change and these resistance states correspond to what you measure by sweeping the magnetic field. So they correspond to the states you measure just in sweeping the magnetic field at zero. So you're inferring the magnetic state through the resistance of the structure, using the jet and magneto resistance effect. So that's quite nice. And if it were just current-induced fields, you might expect that this curve would be symmetric about zero. It's not symmetric, so that's evidence that there's something else going on. About that time, we also did some experiments where we applied high magnetic fields. These are cobalt, copper, cobalt structures where you apply a very large magnetic field. This is the magnetic hysteresis, parallel and anti-parallel for in-plane fields. We applied a very, very large magnetic field perpendicular to the layers, and then applied a current to the sample. And we saw exactly what Maxime Soy had seen in the first Grenoble experiments, that for one direction of the current, we basically had a differential resistance that just gradually increased. But for the other direction of the current, we saw a jump in resistance that's slightly hysteretic. And this jump in resistance corresponds to the magnetoresistance, the full magnetoresistance we measured from parallel to anti-parallel. And what we said in this paper was that this was an indication that the magnet is actually, in the presence of the spin current, is actually looking for a maximum in its magnetic energy rather than a minimum. So if you turn this around, if you change the sign of the damping, you would actually seek a maximum in the energy, like getting the magnet to stick to magnetize anti-parallel to the magnetic field. And this is consistent with this idea. That is, you apply a big enough current at some threshold, you reach an anti-parallel state. And this happens in a very large field. This is in 2 Tesla, but up to 8 Tesla you can achieve a state where the current actually balances, where the current presumably leads to this anti-parallel configuration. Okay. The other experiment, I think, which was very key, was to see that was a noise experiment. You apply a DC current to one of these pillars, and you look with a spectrum analyzer at the resulting voltage fluctuations. So these are, again, these kinds of curves here. So you see this is one of these pillars, a simple cobalt copper permalloy or cobalt copper cobalt. You feed in a DC current and you look at the output. You amplify the output and you look at it on the spectrum analyzer. These are the IV curves. This is differential resistance versus current for various magnetic fields. And here you see the hysteretic response with current, like I showed you earlier. As you apply a magnetic field, you eventually you don't see a hysteretic response, you see little blips in the differential resistance. If you go now and bias the system at one of these blips and look at the spectrum, you see peaks in the spectrum in the gigahertz frequency range. The gigahertz frequency range is the range in which you have, which is the natural frequency of these systems. It's the ferromagnetic resonance frequency. And what they could show is that there are sometimes very sharp peaks at particular values of frequency, which suggests that there's magnetization dynamics going on in a steady state current. So they could show this is the spectrum, frequency versus magnetic field. So the frequency increases as you increase the applied magnetic field, and this is the noise power as a function of current. So not only can you switch the elements, you see that there's dynamics going on in the layers, and that dynamics is in the gigahertz range. There was an experiment just done 5 minutes down the road in NIST, where they didn't pattern the magnetic layers. They had magnetic layers, and they made a contact to the layers, a point contact. So they restricted the current to flow through a small aperture into these magnetic layers, and they saw a beautiful peak in the noise with a very, very narrow line. And this they interpret as the excitation of spin waves in the magnetic. So now we don't have an isolated magnet. We have a continuous film which we're feeding current into in a contact, and this is exciting dynamics. There's noise at the ferromagnetic at some frequency, and the picture is that you're exciting the system locally, but spin waves are radiating away from the contact. So you can excite spin waves by passing current through these magnetic layers. Another very nifty experiment was that people took two contacts, closely separated, just 200 nanometers apart, and showed that you see noise individually from each of these contacts. This is again done at NIST and also at a company, Freescale, which is now called Everspin. You have two contacts, and now you look at the resulting spectrum when these contacts are excited individually, and then when the contacts are excited in some range of current where they have nearly the same frequency. And they saw that these contacts phase lock. So you start with two lines from the two contacts, A and B, and if you adjust the currents, you get a much, much narrower line with a great deal higher power. So you have a range of conditions under which these two contacts know about each other. They're two coupled oscillators, and they oscillate in phase and generate significantly more power into the circuit. So the mechanism by which these contacts are coupled is presumably through the spin waves in the material. So you're exciting a spin wave here, and this contact knows about this one because of spin wave propagation in this layer. If you come in and cut this layer with a knife, a fib, you can show you again have two independent oscillators. So you could imagine a number of ways that these layers could couple. They can couple through the dipole fields. They could couple because they're attached to the same circuit, or they can couple because you're exciting the layer you're exciting a single ferromagnetic layer.
So the question is, what's the range of these spin waves that propagate in the material? So how far can you
that's
couple
a very
these
good
things?
That's a very good question. So if you just take the LOG equations and look at the spin waves are damped just by this alpha, and you would predict that they can travel up to 40 microns. So long distances. So you can excite a spin wave, and so these are not that strongly damped. So these long wavelength spin waves, I guess the spin waves have a wavelength on the scale of a micron, I believe. It depends on the frequency of the spin waves. They can propagate long distances.
They're transporting horizontally.
Yeah, they're transporting horizontally. The current is flowing vertically. It's exciting the region under the contact, and then the spin waves radiate away from the contact.
So you can use that to transport information in your circuit?
You should be able to use it to transport information in a circuit. You should be able to you should be able to transport information through spin waves and propagation.
So usually in the direction perpendicular to your plug.
Actually, in this case, the propagation is in the magnetic field.
Okay.
So what are you actually measuring here that you're taking the power spectrum of?
So you're taking the power spectrum of the combined of the two oscillators combined. So you take you feed the output of these two oscillators, you combine them, you add them, and you send it to an amplifier. And then to your spectrum analysis. So you're looking at the combined power coming out of those oscillators. And so this is the combined spectrum when they're oscillating at different frequencies, and then you adjust them, and in some range they couple, and you see a huge increase in the output power of the oscillators.
Could you also get them to interfere destructively?
You should be able to get them to interfere destructively as well. These, I guess, you could, if you'd have to figure out, you'd have to control the phase of the oscillation. So these are letting the oscillators just run, and they lock. Okay, now if you need to find a way to engineer the coupling to change the phase, or to be able to come in here and add some kind of coupling, add something, namely an AC current. You could do it with an AC current, which would set the phase, which would set a phase difference. This is one class of an experiment. Another class of experiments is you feed in an AC current, and you can show that these oscillators can lock to or anti-lock to an AC drive. So you can control the phase through the way you couple to these oscillators. It is cute. I proposed a device actually along these lines, that you would actually inject perpendicularly magnetized spins and into it. So you'd have a polarizer which is perpendicularly magnetized. The idea is that you have the maximum torque because you're injecting electrons which are perpendicular to the magnetization, and then if this element is symmetric, it will oscillate, and that can give you a large oscillation amplitude. And the other aspect of this was that if the layers had anisotropy, this could provide a very fast means of switching the layer magnetization, because the torque actually tends to rotate the magnetization out of the film plane, and that leads to demagnetization fields about which the magnetization processes, and that can be a very large field. Anyway, I wrote there was a very nice article done by a group, an experiment. They realized this geometry in experiment and constructed an oscillator and showed that this worked. There was a Nature Materials, and then I wrote a commentary on that, some poetry about the result. So if you want to read some poetry, it's there. So this shows you the kind of signal you can get. This is the actual signal in time, an oscillating signal. This is the Fourier transform of the signal. Okay, I thought it's interesting to note that to understand now. I mean, one of the natural questions you can ask is, you have a current now. You have a new way to manipulate the magnet. What about thermal fluctuations? What about the stability of these states when you have a current present? This is not really a solved problem, but of course experimentalists don't care if it's solved or not. They go ahead and measure. And this was work done at IBM, where they looked at the switching time as a function of conditions. So what they did is they would start the system, say, in a particular state, anti-parallel. Then they would apply a pulse of current and monitor the resistance. And they would do that experiment thousands of times and average the results. And when you do that thousands of times, you get the decay of that state and the times and the average switching time of that state.
Are those real oscillations, or is that just noise?
That's likely just noise, actually.
Is the power spectrum that noise being analyzed?
You're talking about this noise on top of it. I don't believe so. These were actually, I would say, these experiments were pushing the limit in terms of resolution. because you're trying to time resolve a signal that's actually very, very small. You have a 1% or change in resistance on top of, and you're trying to make a time resolved measurement of that. Most people, if you told them that, most experimentals, if you told them you wanted to measure 1% change in resistance, they would say you have to have a very narrow bandwidth. You would use a locket amplifier. So these were averaged over many times. So I would guess that this is not just noise in the measurement. That would be my first guess. The main interest here was to look at the average switching time. And what they did is here's the average. So they did these experiments for various currents, and what they did is as you vary the current, you see a behavior like this for the inverse average switching time. You see a very small average, and then the switching time inverse increases dramatically so the rate of reversal increases dramatically. In fact, it depends linearly in this range of currents. So you could say the critical current here is here if you extrapolate down. So there's a subcritical regime and an above critical regime. This is the same data on a log plot. You can see the switching time varies over several switching rate varies over several decades, depending on the conditions. I assume one of these is parallel and one of these is anti-parallel switching. I don't recall. But they were able to understand this data with the following phenomenological model. For sub-threshold switching, if you just leave off this 1 minus I over IC, you'll recognize this is just thermal activation over a barrier, where the barrier height depends on the applied magnetic field. What they added to that was a current-dependent effective barrier. You could think about it as a current-dependent effective barrier or a current-dependent temperature. And they were able to understand this sub-threshold behavior as the current increasing the rate of thermal activation. In the supercritical regime, the rate of switching depends on how far above the critical threshold you are. And that's also straightforward to understand. In the supercritical regime, it's how much angular momentum you can pump in per unit time. So you need to change the angular momentum by a certain amount, and how many electrons you put through per unit time determines how long it takes to switch. So these are the first. So this is the phenomenon. This is the experimental result and the phenomenological model. And then there have been several attempts to go beyond that. Li and Zhang, and Fisher and Apikorov have both written papers analyzing this situation, looking at the dynamics when you have a spin transfer torque and thermal fluctuations. Okay, I'm probably out of time. I'm sorry. I'm going to go. Can I go for 5 more minutes?
Yeah, I have
one.
So yes, I could skip. Let me spend a few more minutes and then I'll move on. The theme this morning was that now we're merging in terms of ability to interrogate smaller systems. And this is now we can actually do experiments where we look at the excitations of an individual magnet through this spin transfer interaction. So normally, what you can do ferromagnetic resonance. You can drive a system with an AC magnetic field, and you can look at, say, bulk systems, thin films, etc. Now, using the spin transfer interaction, you can excite resonance of a nanoscale magnet. How does it work? Instead of putting in a DC current, you can put in a small amplitude AC current. That AC current can be subthreshold and will cause oscillating torques on the magnetization. Those oscillating torques can cause oscillations in the magnetization orientation. And the oscillating magnetization will generate oscillatory resistance changes. And so if those resistance changes are occurring at the same frequency as the current, you'll get a signal that's at DC, if you like. So you're mixing the signals in that small junction. And you can show that with the spin transfer reaction, this in-plane interaction, the mixing signal, the signal near DC, is a Lorentzian, where the width of the line which is centered at the resonance frequency of the element, with a width that's proportional to the damping. And this allows us now to go in and measure the damping of nanometer scale magnetic elements, and also to measure the spin transfer interaction. We can now actually go in and use this technique to actually find out how much angular momentum each electron is putting into this magnetic layer. And we can also crank up the power and excite very nonlinear dynamics. As we've already seen that switching is a highly nonlinear process. So this is an experiment we've done where we have a cobalt-nickel layer and a cobalt layer. They're nearly magnetized. We can magnetize them. This is the magnetoresistance. We can apply a current. We can apply a field perpendicular to the layers. The cobalt layer is still mainly magnetized in plane, and the cobalt-nickel layer is out of plane. And if you measure differential resistance versus bias, there's an excitation at some critical current, 8 milliamps in this case. And what you can do, well, this is a phase diagram. This is now magnetic field current. There's an excitation at about 8 milliamps, a high enough perpendicular magnetic field. But these fields, one layer is in plane, one is perpendicular, and then if you put a microwave current in, you see a peak, and look at the DC voltage. This is actually, the microwaves are actually modulating a low frequency, so they appear as, on a lock. You use a lock-in detection to detect them. You can see a peak in the voltage, which disperses to higher magnetic field as you increase the RF current. So this actually mirrors the FMR mode of the film, and this enables you to determine the anisotropy and G factor, as well as the damping of an individual nanomagnet. This is exactly experiments where with much finer resolution, this is a film, and this is the same film patterned into a nanopillar. You can see there's a shift of the frequency up. And we think what we're seeing is that, so there's a frequency at any given field is a little bit higher in the nanopillar. We think it's because of the mode structure we're exciting in the pillar. If you, in a small element, the fields are no longer uniform, so the modes you excite are no longer uniform. These are the normal modes, the lowest modes of something that has the same shape as our pillar. There's also additional fields associated with the additional layers, our structure that can explain the shift. And we could use this method to measure the damping of an individual element in our structure. Okay, finally. And so this is the kind of things we can now do in the lab. We can explore these elements, and this is getting at dynamics now of very small elements. Why are people so interested in this? Well, one reason is you can, if you make an element smaller, it typically gets less stable. So you have this conflicting requirement, which we heard about this morning, that you want the element to switch in a really modest field, but to be very thermally stable. Now, with spin transfer, you can switch very, very high anisotropy elements with modest currents. So the idea is you can take an element that's very thermally stable and switch it with a current. And that's one of the interests, is that in principle you can make very, very small elements that are thermally stable. And the basis for this is what I talked about in the talk. You put in an anisotropy that gives you an energy barrier of 40 kBT, which is what you need for storage for 10 years or so. And then you calculate what the critical current would be for that element. And then it turns out to be given in terms of the parameters, the energy. You can write the critical current as directly proportional to the energy barrier, where the proportionality depends on the damping. And one of the reasons this works is the damping of these elements is reasonably small. And you find that if, just setting the energy to be 40 kBT, that you can switch elements with currents in the order of 50 microvolts. So that gets interesting because a transistor can supply, a very small transistor can supply this kind of currents. So you can imagine a transistor per bit, per magnetic element, switching these elements and thermally stable, very small elements. Okay, so hope I've taught you something that you found interesting. That you can reverse magnetization, you can cause precession, you can excite spin waves. There are many basic questions. I mean, there's questions from the transport side. How do you understand the interactions between currents and magnetization? There's micromagnetics. How do you include these interactions in micromagnetics? How do you understand noise when you have spin currents? There really is a great variety of phenomena. I haven't really spoken about everything. There's current-induced domain wall motion is a major effort in a number of laboratories, and there are really new types of devices that can operate, which is one of the reasons this is an area that's growing in experiment and in theory. Thank you.
Questions? I think you mentioned this before. So right now in your spin torque device, you have a continuous channel. So if you replace them by tunnel junctions, what will be the key differences?
Right now, you're saying the intermediate layer is a metal, right? There's a great interest in actually replacing that metal with a tunnel junction, and the reason is the resistance change is much larger with the magnetic tunnel junctions.
Would be Coulomb blockade or?
These at the scale of 100 nanometers, there's not. You're kind of beyond the Coulomb blockade, and these. I mean, maybe at very low temperature you would have Coulomb blockade, but the interest in terms of is in applications. Tunnel junctions provide a much larger signal. The issues are that now you have to provide a large current to a tunnel junction. And so the issues are practical. These junctions break down at some threshold. So the breakdown voltage has to be larger than the threshold needed to excite the structure. I mean, the interactions are basically what I wrote down earlier. The main difference from the physics is now it appears that the perpendicular torque is important in magnetic tunnel junctions, whereas in metals, I guess you could think about it as with metals you have some averaging over the Fermi surface, which kind of erases this perpendicular torque, but in a tunnel junction you have a strong preference for electrons moving perpendicular to the barrier, so you don't have that kind of averaging. You average differently over the Fermi surface, and apparently that makes a big difference in the kinds of torques that appear in magnetic tunnel junctions. Physics is, in terms of dynamics, a lot of the same kinds of things. You see precession switching, and that's there's a lot of effort going on there.
Any other question? So let's find